Welcome to this respiratory e-lecture. This is the first part of 3 parts. Feel free as you get through each part to stop, make your own notes, make sure that you understand the content before moving on to the next part. If you have any queries, feel free to email me, or if you just want clarification on a point. So, the learning outcomes for the whole of these 3 parts. In this part, we're going to talk about the functional zone. So we're talking here about the conducting zone, and we're talking about the respiratory zone of the respiratory system. We'll also be talking a bit about the gas laws. Then we're going to look at the 4 main respiratory processes. Pulmonary ventilation we'll do in this bit. Transport will be covered in part 3, even though it's second on the list, because in part 2 we're going to look at external and internal respiration, and it just works a little bit better that way. As I said, we'll talk about the gas laws in this section, and we'll talk about pressure gradients. The nervous and chemical control of respiration, part of that is the normal nervous neural stimuli for respiration that we'll talk about in this section. But then when we get to part 3, we're going to talk about the chemical control and how that then impacts on the neural control to change respiratory rate and depth. So these are the 4 main phases or processes that make up respiration. Pulmonary ventilation, external respiration, which is diffusion of the gases across the respiratory membrane, transport of gases around the blood, and internal respiration at the cellular level. And of course, all of this, the upshot of it all, is cellular respiration that we talked about in cell biology. So this is why we need the oxygen for the aerobic parts of cellular respiration, and also where the CO2 then comes from as a result of the metabolism of that oxygen. So we have 2 different zones in terms of the respiratory system. The first really is the conducting zone. This is where air as a compound gas moves through. So of course it starts at the nose, the mouth, down the pharynx, larynx, trachea, and finally into the bronchioles. So this is differentiated as the conducting zone. The respiratory zone, on the other hand, this is where we start to get the diffusion of gases, individual gases, so oxygen and carbon dioxide, across membranes. So this includes the little tiny bronchioles, the alveolar ducts that lead to the bunches of alveoli, and the alveoli themselves. The lungs, of course, have millions of alveoli, and these alveoli necessarily are covered in a network of capillaries to bring in deoxygenated blood and take away oxygenated blood. So the conducting zone, of course, the main function of the conducting zone is going to be to conduct air. But it has other functions if you think about it. We've got the prevention of foreign bodies, so we've got the gag reflex, we've got the epiglottis. It also purifies, so we've got nasal hairs, we've got mucus and mucociliary clearance, if you remember. And it warms and humidifies, and in some ways this is quite important because heating gases increases gas pressure. Part of this is because we've got this rich blood supply to the mucous membranes that help to warm and humidify. And as we said, of course, the main thing is about air entry. So to keep that patent, we've got these 15 to 20 C shapes of cartilage along the trachea. The opening of the C, of course, being towards the back where we've got the spine. The conducting zone also controls the volume of air. So if we have bronchodilation, which is usually due to the sympathetic nervous system or other inflammatory mediators, if you have bronchodilation, you're going to get more air in. If you have bronchoconstriction, of course, that's going to reduce the conduction of air. The respiratory zone basically has one function, and this is all about the exchange of oxygen and carbon dioxide between the alveoli and the blood. Okay, so let's talk about air. Pulmonary ventilation is all about the inspiration and the expiration of air. So we need to look at the composition. Well, we can ignore nitrogen. So really what we're looking at are these two, aren't they? So if you look at atmospheric air, we have 159, usually termed 160, for oxygen. And we have some carbon dioxide. Now bear in mind this is at normal sea level, but we accept that atmospheric air, unless you're going to run up a mountain and go very, very high, it is not going to change realistically. So that is a set pressure. Alveolar air, on the other hand, if you look at it for oxygen, on the chart we're talking about 104, but we generally refer to it as 100 because it's an easy figure to remember, and 40 for CO2. We'll come back to these figures, they are quite important. So the question is, why are the two different? Well, remember we said about humidification? Well, water vapor tends to dilute the alveolar gases for a start off. The other thing, and again this is an important thing to remember, only 1/7 of alveolar air is exchanged, replaced, every time we breathe in and out. And this means that we don't have these sudden changes in blood gases, but it keeps those figures constant for alveolar air. Oxygen, of course, is constantly absorbed from the alveolar air. So when we breathe in air, we take oxygen out of it and put it into the blood and take it off to the tissues. Conversely, of course, CO2, because of cellular respiration, we're producing CO2, has to go back in the blood, goes back towards the lungs, diffuses into the alveoli, and is then exhaled. So CO2 is constantly being pulled out of the body. So gas pressure then. Gas pressure is caused by these molecules, the molecules are of a gas, colliding with the walls of the container. The molecules are said to have kinetic energy, and this is about Newton's laws of motion. Basically, a molecule is bumbling along, it runs into another molecule, and that molecule continues. The energy transfers, the molecule who's been bumped into carries on travelling until eventually they all start hitting the walls of the container. You imagine you're running down the street, you run into someone, they will carry on with the momentum of your running, and this is what's happening with these molecules. This is summed up really in Boyle's law, and yes, he's the man of the anaesthetic machine. What he said was, if you increase the size of the container, the pressure of the gas inside will reduce. This is presuming the amount of gas stays the same. If you reduce the size of the container, the pressure of the gas inside will increase. If you think about Waterloo Concourse at rush hour, you've got lots of people all running around. Suddenly you put up some barriers. You make the space smaller. It's more likely that those people will run into each other, bounce off the walls, etc. You take the barriers away, they can spread out. Less likely they'll bump into each other, less likely they'll hit the walls. So how does this relate to respiration, and in particular what we're talking about, pulmonary ventilation?
Okay, so Boyle's law. Boyle's law is all about volume and pressure. So as volume goes up, pressure goes down, and vice versa. So if I have a big gas canister, there it is, there's its little monitor on the top to say what's in it, and in that gas canister, I have a certain amount of a gas, air. Let's have air. So here's my air bumbling around in my canister. Lots and lots of air in my canister. Okay. Now, you can see this air in this canister. There's quite a lot of space around it. So a bit like the analogy of Waterloo Station, when it's fairly open and quiet, people don't bump into each other, and the same thing happens with molecules. So we can have this molecule go off that way, hit that molecule, a bit like snooker balls. This one might go off in that direction. It's less likely, so say we have this one, it can happen because that's what gives us the pressure. It can hit the sides, giving us the pressure. But in this size container, it's less likely to happen, so we have lower pressure. So our gauge might be there. Okay, if I take the same amount of gas and I put it in a smaller container, there's my smaller container. Now, I don't know how many molecules of gas I've got in there, so I'm going to approximate. I didn't count them. If I put the same amount of gas into this container, lots and lots, there, you can see what's going to happen in terms of them bumbling around off each other. So in this scenario, I have the situation where that one could move, it'll hit that one. This one is more likely to hit the sides. It might go up and hit that one. That one will hit the sides. But you get the general idea. If we hit that one may shoot off and hit the sides. It may not. But it is more likely to hit the sides, which will give us increased pressure. So our pressure gauge might be up there. So, okay, this is all very well. We're talking about canisters, yeah, but we're talking about lungs here. So, okay, in terms of the lungs, here's a nice pair of lungs. Here we go. They may not be symmetrical, but you get the general idea. Lungs have an opening. It's got a bit of a case of bronchoconstriction. Let's take away the bronchoconstriction. But lungs have an opening. So this is where we start to get pressure gradients developing. So again, if we've got air in our lungs, so here's our air. In both lungs, hopefully. And it's at a certain pressure. Now, the outside, so if we go outside the lungs, of course, we're talking about atmospheric pressure. So atmospheric air pressure is always 760 millimeters of mercury. millimetres Hg. I say always, obviously if you go up a long way up a mountain, it will change. But at sea level, we're talking 760 millimetres mercury. So, okay, if it's the same in the lungs, so say we have 760 millimetres of mercury in the lungs, we don't have a pressure gradient, do we? So what's going to happen is nothing. Air will not move in, it will not move out. But here we go back to this concept of smaller and larger containers, because of course, when we breathe out, our lungs get smaller, the thoracic cavity gets smaller, the lungs get smaller. So we're effectively going to this smaller bottle. So they get smaller. If they get smaller, volume decreases, Boyle's law, so therefore pressure will increase. So if we put our pressure here, say up to 762, let's have, not by much, this is greater than atmospheric air pressure. Pressure gradients, what's going to happen? High to low, so air will move out of the lungs to the atmosphere because it's following its pressure gradient from high to low. And if you think, you breathe out, you can feel air's coming out. And that's exactly what's happening when we make the lungs smaller. Okay, conversely, if we make them bigger, again, when we inhale, make the thoracic cavity larger, we make the lungs larger, we're going back to our scenario of a larger gas canister, aren't we? So we make them larger, we've got greater volume, therefore, what's going to happen to our pressure? Yeah, absolutely, our pressure is going to go down. So if it goes down, say in this case, to about 758 millimetres of mercury, then we've got a pressure gradient again. But this time, high to low, air is going to move into the lungs, following its pressure gradient until it equalizes and we have no more pressure gradient.
So remember, gases follow a pressure gradient. This is a pressure gradient, not a concentration gradient, or an electrical gradient for that matter. A pressure gradient. And they move from a high pressure area to a low pressure area. So in pulmonary ventilation, when the lung volume expands on inspiration, air pressure in the alveoli decreases. It decreases to the point where it is less than atmospheric air. We're talking about a very small difference, but still it's less than atmospheric air. This creates a pressure gradient and air will move into the alveoli following its pressure gradient. When the lung volume decreases on expiration, so the volume decreases, therefore the pressure increases in the alveoli. Of course, air pressure in the alveoli is now greater than atmospheric air. Remember, atmospheric air pressure can't change. And this creates a pressure gradient in the other direction. So air moves outwards from an area of high pressure to an area of lower pressure. So pulmonary ventilation involves creating pressure gradients. Between inspiration and expiration, atmospheric and alveolar air pressures are equal. That gradient has equalized. We don't have a gradient anymore. They equalize at 760 millimeters of mercury, and that is atmospheric air pressure. As per Boyle's law, if you increase the volume of the thorax, the air pressure in the lung will reduce. Increase volume, then we reduce the air pressure. This gives us the pressure gradient between atmospheric and alveolar air pressure. Of course, to do this, what we need to do, we need skeletal muscles to contract and relax in order to change that thoracic volume. This involves a neural control, so we're talking about action potentials being sent to neuromuscular junctions. You remember neuromuscular junctions, ACH is exocytosed, etc., from the respiratory centers in the medulla. So, in order to get those action potentials down to the skeletal muscles, we need some sort of neural control, some sort of stimulus, the origin of these action potentials. It is subject to a lot of research and a lot of controversy, and ideas over the last 10 years or so have changed quite a bit. It involves complex interactions of multiple nuclei in the pons and in the medulla oblongata. Remember, nuclei are just little bunches of neural somas, somata, the cell bodies and synapses. The central pattern generator, or CPG, is thought to be something called the pre-Botzinger complex, and this is in the ventral medulla, the front of the medulla. Expiration, on the other hand, is thought to be stimulated by the Botzinger complex itself rather than the pre-Botzinger complex, and this is next to the pre-Botzinger central pattern generator. But all of this is moderated by multiple inputs, multiple action potentials, afferent action potentials coming in from the pons, so the pontine respiratory center, and the medullary nuclei. Because of this, pre-Botzinger cells can't really be considered to be true pacemaker or true autorhythmic cells. So just so we know what we're talking about here, here's the brain. You can see you've got the pons in the brainstem, and below that you've got the medulla. This is where we find these respiratory nuclei. And within the ventral medulla, we find the pre-Botzinger and the Botzinger complexes. So within the medulla, we can divide the respiratory centers into two parts, really. The ventral respiratory group we've just talked about at the front in the medulla. This is where we have these autorhythmic type neurons that drive inspiration, our pre-Botzinger complex. We also have inhibitory neurons, this is our Botzinger complex, that inhibit inspiration. And of course, when that happens, it causes expiration. Behind that, we have the dorsal respiratory group. The dorsal respiratory group, it regulates the ventral respiratory group, so we've got lots of little interneurons communicating between the two. Because it regulates the VRG, it also regulates respiratory rate and depth. And it does this because it receives inputs from various mechanoreceptors and chemoreceptors that we'll then talk about in part 3. The pontine respiratory center in the pons is more about fine-tuning. So this modulates and it changes the pattern of breathing through synaptic inputs to the VRG, and it does this to cope with speaking. If you think about it, when you're speaking, you need to change and modify how you're breathing to cope with speaking. And also it has an input in changing respiration when we're exercising.
Okay, so let's talk about the neural control of respiration. So if we have our brainstem, we have the pons, and then we have our old friend, the medulla. So here's our pons, and below it, the medulla oblongata. We're friendly with it, so we'll just call it medulla, right? Okay, so within those, we'll start at the top. With the pons, we have the pontine respiratory center. Pontine respiratory center. Below it in the medulla, we have 2 respiratory centers. So in this case, at this back, we have the dorsal respiratory group, or DRG. And we'll talk about the pontine and the DRG and what they do in a sec, but let's talk about first about our ventral respiratory group. So, of course, ventral, you'd expect it at the front. So here we have our ventral respiratory group, VRG. Yeah? As we know, this is split into 2 parts. So at the top, we have the part known as the Bertzinger complex. Mustn't forget the umlaut. Below it, we have what's known as the pre-Bertzinger complex. Yep. And that's our ventral respiratory group. Okay, in terms of inspiration, as we know, the pre-Bertzinger is our central pattern generator. This is where we have these sort of autorhythmic cells that will give the stimulus for respiration. So let's have a pair of lungs. Well, let's have a thorax. Have to forgive me, this is going to be slightly stylized. Some ribs. We're not going to have as many as we would normally have because this is an abstract thorax. Between the ribs, we have the external intercostal muscles. Not internal. Internal intercostal muscles are actually involved more in forceful expiration. They're accessory muscles. So these are our external intercostal muscles between the ribs. Our other muscle, of course, it's still a muscle, is the diaphragm. So below that, we have the diaphragm. So external intercostal muscles. And these are skeletal muscles like any other. And here we have our diaphragm. Okay, so let's link these two together neurally. So from the pre-Bertzinger to the external intercostal muscles, we have the intercostal nerve. Easy to remember, intercostal nerve. Intercostal. N for nerve. Also, to the diaphragm, we have the phrenic nerve. So off we go to the diaphragm from the pre-Bertzinger complex with the phrenic. And both of these are efferent nerves. Yes, so action potentials are coming out. They come out, they're sent out by the pre-Bertzinger complex along these nerves to both sets of muscles for 2 seconds. So we get 2 seconds of action potentials going to the muscles. Go to the neuromuscular junctions, and we get excitation, contraction, coupling. The diaphragm contracts. When the diaphragm contracts, it flattens out. If you think of it as normally a dome, if it gets smaller, it's going to go flatter. So the diaphragm flattens out and moves down. The intercostal muscles, when they contract, they move the ribs up and out. If you take a big breath, you can feel that happening. So we go up and out, up and out. So what we're effectively doing here is we're increasing the volume of the thoracic cavity. When we increase the volume of the thoracic cavity, the lungs follow. The volume of the lungs increases. Because we're creating that pressure gradient, air moves into the lungs. So we have a little pause when we get to the point of equalization of air. After that, so that was inspiration, after that, we need to have expiration. And this is where our Bertzinger complex up here comes in, because what it does, it sends IPSPs, inhibitory postsynaptic potentials, to the pre-Bertzinger complex. And what this does, it blocks these. If it blocks action potentials going along these nerves, then it will block excitation, contraction, coupling, and we get relaxation. So what happens, our diaphragm moves back into its classic dome shape. Our ribs move back down and in. And this blocks this for about 3 seconds. So during that 3 seconds, the volume reduces again, the lung volume reduces again. Because we've created a pressure gradient, of course, air is going to move out because we've increased the pressure in the lungs by reducing the volume. Okay, so that's inspiration and expiration. So action potentials for 2 seconds from the pre-Bertzinger, then we get inhibition from the Bertzinger for 3 seconds that gives us relaxation, everything gets smaller. Then we have another pause. When we start to talk about regulation, what we're talking about is these other respiratory centers. So remember we have the pontine. Now the pontine is all about the phase alteration to allow for speaking. I'm doing it now. My pontine respiratory center is allowing me to do this. So we have modulation coming in there. The dorsal respiratory group takes in all the information about what's happening with blood gases, and we'll talk more about that in part 3. And it also modulates what's happening with rate and rhythm to adjust the blood gases. And that's the neural control of respiration.
So what exactly happens during pulmonary ventilation? Well, first, we get spontaneous depolarization. This is in the inspiratory nuclei, or the central pattern generator, known as the pre-Botzinger complex. And this is in the ventral respiratory group. Action potentials are then sent down the nerves, and specifically the efferent phrenic nerve to the diaphragm and the intercostal nerve to the external intercostal muscles. They last for about 2 seconds. As a result of this, remember skeletal muscle excitation and contraction, the diaphragm and the external intercostal muscles contract. The diaphragm, because it's normally dome-shaped, as soon as it gets smaller, it flattens out. Also, the ribs move up and out. And you can imagine what this is going to do. This is going to increase the volume of the thoracic cavity. The lungs, because hopefully they're attached to the walls of the thoracic cavity, also expand. When they expand, they're going to increase the volume in the alveoli. If you increase the volume, you decrease the air pressure within the alveoli. It becomes less than atmospheric air pressure. Consequently, air moves from an area of high pressure to low, so it moves into the lungs. Once those air pressures have equalized between atmospheric and alveolar air, and it takes a little bit of a pause to do that, after that, we get spontaneous depolarization in the expiratory nuclei. So this is our Botzinger complex, also within the ventral respiratory group. This creates IPSPs, inhibitory postsynaptic potentials, in the phrenic and intercostal neurons for about 3 seconds. And of course, because they're inhibiting any action potentials, they're inhibiting contraction, so they are effectively causing relaxation of the diaphragm and of those external intercostal muscles. The diaphragm and the external intercostal muscles relax, and when they relax, the thoracic cavity gets smaller and the lungs recoil. We've now reduced the volume in the lungs, which has increased the air pressure in the lungs greater than atmospheric. Following its pressure gradient, air moves out of the lungs now into the atmosphere. There's another pause while this happens and the air pressures equalize, and after that, of course, inspiration starts again.
Okay, so let's just go over again what happens with those pressure gradients in terms of inspiration and expiration. In between those, we have pause. So remember at our pause, there's our lungs. Our pressures are equalized. So within the lungs, we must be the same as atmospheric, 760 millimeters of Hg. Atmospheric, 760 millimeters of Hg. And remember, That doesn't change. So at this point, we've got no pressure gradient. Because we've got no pressure gradient, we have no airflow. And if you think about when you breathe in and you breathe out, you always have a pause in between, and that's when those pressures equalize. So at this point, we have no airflow. Okay, so we had our little pause, but now we need to breathe in again. So we increase the volume. So here's a slightly bigger pair of lungs because we've increased the volume. In our bigger lungs, greater the volume, so we've increased volume. So what's going to happen to pressure? Pressure is going to decrease. Boyle's law. Decrease pressure. So you remember we said before that we're talking about very, very small changes here. So if we're decreasing the pressure, let's make it 758 millimeters of mercury. Atmospheric stays the same. So 760 millimeters of mercury. Okay, we've got a pressure gradient, haven't we? High to low. Remember, air moves from high pressure to low pressure. So if we're talking this being 758, this being 760, air is going to flow into the lungs. And we know this happens because we know this is what happens when we breathe in on inspiration. So this is inspiration. Okay, then we go back to this scenario because these pressures equalize. So the lungs reach a pressure of 760. And we have a pause before we breathe out again. When we breathe out, as we know, the lungs get smaller. So we'll have a smaller set of lungs. Make them really diddy. They also seem to have moved further apart. So we've got a smaller set of lungs and we've reduced the volume. If we've reduced the volume, we've increased the pressure. So we've got increased pressure within the lungs. So, okay, this was our pause, 760. We've now increased the pressure a bit above that. So let's have 762 millimeters of mercury. What does atmospheric air pressure do? Yes, it stays the same because between breathing in and breathing out, I haven't just run up some very high mountain. So it stays the same. 760 millimeters of mercury. Again, we've now got a difference, therefore we've got a pressure gradient, but in this case, our area of high pressure is the lungs compared to atmospheric pressure. So, movement of air, high to low, air is going to move out of the lungs. And again, we know this happens because this is what happens. When we breathe out, air moves out. And that is pulmonary ventilation and the pressure gradients.
So let's do a recap of pulmonary ventilation. First of all, we'll talk about inspiration. So between expiration and inspiration, air pressure between the atmosphere and the alveoli is equalized at 760 millimeters of mercury. Then the phrenic and intercostal nerves are stimulated by these action potentials from the ventral respiratory group, from that pre-Botzinger complex. The diaphragm contracts and descends, and the external intercostal muscles contract, pulling the ribs up and out. The lungs then expand to fill this new expanded volume, and consequently the volume in the lungs increases. Because we've increased the volume, the air pressure within the alveoli drops, and it drops to approximately 758 millimeters of mercury. Therefore, because we've dropped it in the lungs, atmospheric air pressure, which remember doesn't change, becomes greater than alveolar air pressure, and this creates our pressure gradient. Air flows down its pressure gradient into the alveoli from the atmosphere. After approximately 2 seconds, the air pressures between atmosphere and alveoli will equalize. So expiration then. Remember, we've had inspiration, we've had airflow in, the air pressures between atmosphere and alveoli have equalized. When pressures equalize after inspiration, there's a pause. The length of the pause is going to be controlled. It's a bit like the delay at the AV node in cardiac autorhythmic pathways. You get a pause, and that's going to be dependent on respiratory rate. The expiratory nuclei in the VRG, remember this is our Botzinger complex, creates these IPSPs in the inspiratory efferent neurons and inhibits them, stops the action potentials, stops contraction. Without any action potentials getting to them, the diaphragm and the external intercostal muscles relax. The diaphragm rises back up to its dome shape, the ribs move in and down, and we reduce thoracic volume. As a consequence, of course, the lungs now recoil as well, and we are reducing the volume within the alveoli. Alveolar air pressure, as per Boyle's law, increases, and it increases to about 762 millimeters of mercury. So not a massive increase, but enough. So this is a few millimeters of mercury greater than atmospheric air pressure. So air follows its pressure gradient and moves out of the lungs from high to low. At equalization, so at this point, our pressures in the alveoli and pressures in the atmosphere have equalized. There is a pause before inspiration starts again. Well, that brings us to the end of this first part of the 3-part lecture. If you are confident that you've understood the content and you've made your own notes, then please move on to part 2. If you have any queries, then please email me. As you know, my email address is on Moodle and in the module guide.